Welcome to HAO Colloquium. Our speaker today is Hannah Strecker from Instituto de Astrofísica de Andalucía in Granada, Spain. Hannah completed her master's thesis in October 2015 from University of Freiburg on the evolution of the mode flow around sunspots, supervised by Wolfgang Schmidt and co-supervised by Nazaret Bello Gonzalez. She received her PhD in March 2020 from the University of Freiburg and Leibniz Institute for Solar Physics on the decay of sunspots, supervised by Wolfgang Schmidt and co-supervised by Ralph Schlessenmeyer and Nazaret Bello Gonzalez. During her PhD, she closely collaborated with Matthias Rempel in the analysis of his 3D Nudum sunspot simulation. Since January 2021, she is a postdoc in the Solar Physics Group at Instituto de Astrofísica de Andalucía in Granada, Spain. Her main activities include being part of core team for data analysis and calibration of polarimetric and helioseismic imager on board of Solar Orbiter, focusing on the calibration of data of the full disk telescope and involved in the early science preparation. And also the participation in the planning of operations as one of the point of contacts for HAO PHI, the Solar Orbiter Polarimetric and Helioseismic Imager. Today she will be talking on I forgot the title of her talk. Instability of sunspots. So I'll turn it over to you, Hannah.
Thank you. I will share my screen. And go to the presenter mode and hope that you're able to see this now. Is this fine?
Yep, it's good.
Okay, great. Thanks. Thanks for this nice introduction and the possibility to present a work which I started in 2018 during a stay at HAO in collaboration with Matthias Rempel. And I'm very happy that I have the ability now to present some results which we got and which we published at the beginning of the year about the stability and instabilities or instability layers of the subsurface region of sunspots. Sunspots are non-stationary phenomena which are visible as dark magnetic patches on the solar photosphere, and you can see here one down. Are you able to see my cursor? Do you see my cursor? Or
not sure. I don't think so.
Yes.
Oh yeah.
Okay, great. So you see here one sunspot and one observed sunspot in high resolution, and sunspots have an observed lifetime of several days up to several weeks, and therein the evolution of the sunspot, when studying the evolution or especially the decay process, one mostly focuses on the evolution of the total area, which would be the area enclosed here in this spot on the right and the red boundary, or the magnetic flux, which would be in the magnetic field, the magnetic flux contained here in this red contour. However, besides this, the evolution of the flux tube below the surface is not really known and cannot be observed. What we know is based on models, and most models basically agree that the flux tube diameter of a sunspot increases towards the solar surface, which is due to the fanning out of the field lines, as one can see it here in the models, which then leads to the penumbra filamentary structure and this horizontal field in the penumbra, which you see here in the model and also here in this high resolution image. In the inner part of a sunspot, this inner dark core called the umbra has more vertical field. A fully developed sunspot is known to be surrounded by an horizontal outflow or radial flow, which you see here in maps of the line of sight velocity as this blue and red pattern, which is known as the mode flow. The mode flow is assumed to rise below the penumbra and be directed to the horizontal due to the funnel shape. Besides this, the structure and evolution of the flux tube of a sunspot below the visible surface is mainly unknown. Latest increase of computational abilities has given us here more insight as we're able to calculate simulations. For our study, we therefore made use of one of the largest high-resolution simulations, which was calculated with the Muram MHD radiative MHD code by Matthias. And where you can see here the horizontal extension in intensity of the full simulation domain, which has a size of 98 times 98 square megameters, with the sunspot being localized in the center and having an average diameter of 30 megameters. The initial flux tube is therein inserted in or as a circular flux tube in an hydrodynamic environment. The vertical extension of this simulation is 80 megameters, where 700 kilometers show the solar atmosphere, which leaves us with more than 17 megameters of the upper convection zone to study the flux tube of the sunspot. For our analysis, we use a dataset of 30 hours with a cadence of 15 minutes, which provides us 120 time steps. The full simulation run, however, is much longer. And we start our analysis 15 hours after the initialization to give the sunspot and the environment time to adapt. The horizontal resolution of the simulation is 96 kilometers and the vertical resolution is 48 kilometers for the setup we use here for the analysis. Matthias already compared in his publication in 2015 the sunspot's fine structure and the dynamical behavior with the characteristics we know from observation and found that we have a good agreement here. For our analysis of the flux tube, we now made use of maps of the magnetic field. You can see here maps of the magnetic field for 6 different depth positions for the first time step. And I would like to note that we only have a cutout here of the full field of view of 50 times of the full simulation domain of 50 times 50 square megameters, which gives the sunspot flux tube here a larger appearance than it was in the intensity maps you saw before. In this highest layer, which you can see here, 1.25 megameters, we still have a bit the structure of the sunspot, so the highest field strength within the inner part, and then a decreasing one where the pattern becomes a bit more grayish, the weaker field, which resembles a bit the filamentary structure, which we know from the surface. In the surrounding, we see a network pattern, which becomes in the deeper layer similar to the network we know from observations, and a field-free region in the surrounding caused by the mode flow. If we now focus on the flux tube, we see something which we didn't expect. As I said, in the initialization, the flux tube was inserted as a circular monolithic shape. However, as you see here, also the average diameter gives it a round shape. We have large indentations at the boundary, which penetrate then deep into the main flux rope. This is most pronounced here at 3.75 megameters and is a bit weaker in the deeper layers, where the flux tube here appears more compact. However, it's still not a circular shape. We can now look at the evolution in time and see there in the surrounding the action of the mode flow. So now we see this horizontal outward transport of the magnetic patches, which accumulate then as this network structure in the surrounding. However, we would like to focus now on the evolution of this main flux rope, and there we see that this flux tube largely changes in shape. These indentations increase in depth and penetrate deeper into the flux rope, and this is most pronounced in regions from 5 to 10 megameters, while we still can see also that this happens in the deeper regions below 10 megameters, but here the process is way smaller, as you can see. So it's mostly pronounced if you compare now this last figure, and then if you remember the first and the last one, that here also indentations form, which are not as sharp as in the higher regions. This is now a pretty nice visual impression. However, we wanted to study this reshaping in a more quantitative way. And therefore, we had to perform several steps, which was the first, the determination of the boundary or of the outline of the flux tube, which you already just saw as this golden line, however, which was not straightforward to obtain. With the boundary or outline of the flux tube, which we then have, we applied two different methods to analyze the flux tube evolution and its stability in the upper convection zone. One was to look at the relative change of the relation which we have between the parameter of the flux tube and its area. And in a second step, we applied a linear stability analysis. Combining both results gave us then a picture of the unstable or stable layers of the sunspot flux tube in the upper convection zone. For the determination of the flux tube boundary, we decided to focus our analysis in the following on defined depth position with a step size of 0.625 megameters. In general, when one defines the outline of a sunspot, one makes use of the intensity threshold in comparison to the quiet sun. However, as we only use maps of the magnetic field, we had to come up with a different definition or threshold value. And therefore, we made use of the maximum magnetic field strength of each depth position and of all time steps, and averaged for each layer this value in time, and then in addition applied spatial averaging around this respective selected depth position of 5 grid cells, which is averaging of 240 kilometers around each of the selected depth. And then, as this value is still pretty high, as we use the maximum magnetic field strength to yield the threshold to the much weaker field at the boundary of the tube, we divided this value by 2 times E. So we obtain a value which depends on the depth, however, which is similar for all times. You can see the obtained values here as these red crosses in the plot, where I've in addition plotted the black dots, which are the averaged maximum magnetic field strength, so the temporal averaged magnetic field strength divided by 2 times E, but not spatially averaged. As the later analysis depends on our later analysis depends on the definition of this sunspot flux tube outline or boundary, we went to have another test method wherein the boundary is determined with different values. And these values we just determined by an, as we call it now, automatized method, as I just compared for the different layers, the time steps, and applied different values, and choose the one which, according to my eye, fitted best the outline of the tube. Also, the values differ, especially in these deeper layers, when plotting the contours on top of each other in maps of the magnetic field. They fit pretty nice or match fairly well for most of the time steps, which tells us that we are really at the position where we have the largest gradient of the magnetic field. We will later see that this matching changes a bit in the evolution. Yeah, this is a later step. In the following, I will mainly focus on the analysis which we did with this automatized method, as we did this for the steps position, as I said, for 0.625 megameters, while we only did the non-automatized method for steps of 1.25 megameters. However, I will also present as variation some of these results. Applying now the contour or threshold values to all maps of the magnetic field strength, and determining the contour or boundary of the flux tube for all the depth positions, we can come back to our quantitative analysis of the evolution of this geometrical structure. And to do so, we compare now, or we came up with the idea to compare the evolution of compare the area and the length of this contour which we have, and then later compare the obtained values in time. The definition which we came up with is here such that the parameter is the ratio of the circumference, which corresponds to a circle with the area A, where R is the area enclosed into this into the contour, and the length of the contour. So basically, we are comparing two lengths, or two lengths. The advantage of this definition is that for a circular cross section, so if you would really have a circular tube, we would have a value of 1 for our parameter, which we define as the compactness. And another advantage is that it is independent of the diameter of the flux tube, which, as you can see here, for the different, and as we expect, it changes with depth, and therefore we can, when calculating the compactness, also compare the different depth, the results for the different depths. We applied this equation then based on our obtained outline to all time steps and all the depth positions we selected, and found that we have an almost constant compactness down to a depth of 1 megameter, which is now for our 18 megameter deep box, not really deep. And I've shown here the evolution in time for the compactness for the surface layer with the red crosses. You can see that we have a large deviation from a circular tube, where we would have a value of 1, should have a value of 1, which contradicts now a bit to our visual impression, which we had in the intensity maps. However, which can be explained by considering also this huge scattering by the fast evolution of the filamentary structure of the penumbra at the outer boundary. If we look at deeper layers, we find that we have the smallest initial compactness at 3.75 millimeters, given here by this red crosses in this panel. And which means that here we have, when we start our analysis, the largest deviation from a circular flux tube, while deeper layers and higher regions have a more circular shape. In time, we find that for all depth, the compactness decreases. This we have highlighted here also by a linear fit, and we use this linear fit now to be able to compare the how fast this loss of compactness or this the increase of the indentation happens in time. Therefore, we calculate the time when the initial compactness, so K0, has decreased by a factor of 1 divided by E. The obtained values are shown here. We have plotted the depth on the x-axis with the surface layer being here on the right, and the degradation time on the y-axis, starting here only after 2 days, where I would like to note that the degradation time does not mean that the flux tube has dissolved within this time, but instead it means that the shorter the time, the faster the degrade or corrugation or degradation of the flux tube happens. I've in addition plotted here now the values which we obtained with our test method to see how these values match, where we find a good agreement. However, I would highlight the regions or the deviation here in the region between 3 to 5 megameters, because if you look at the plotted contours, we see that starting from 20 hours on, we obtain a deviation when plotting the contours on top of each other. As we expect, the red contour here is always a bit more inside the tube than the blue one, as the red one had higher layers, with higher values, which means that any weaker field is excluded. However, here, this leak causes the exclusion of this large patch here and this large patch here, which by a visual impression one would include or still connect to the flux tube. This separation of these patches here, which also happens, which happens in regions in between 3 to 5 megameters, and which processes on for the later times, tells us that we have here a weakening of the magnetic field, which was not there in previous times. Based on this, one might have to consider this steep increase here with caution, and it might be more liable that the increase is a bit smoother given by the blue values. However, for both methods, we find that the shortest degradation time, which means the fastest evolution, happens in a depth in between 6 to 10 megameters below the surface. Besides this, we find that for all the depth, the structure of the flux tube becomes corrugated, which means we have a reshaping from circular to a corrugated structure with which gave us the idea that the flux tube seems to lose its stability or hints to an ongoing instability mechanism acting. And this responsible mechanism, which we find, is interchange instability. Interchange instability is caused by a perturbation at the boundary of the flux tube, which causes a displacement of magnetic field. If one has, in an idealized case, which we should initially have had in our simulation, a cylindric tube, as you can see it here by the dashed line, and this undergoes the perturbations at a boundary, we obtain a displacement with the field moving from an originally magnetized region to an originally more non-magnetized region. Therein, in this case, we obtain such a fluted structure. This is why one also calls this interchange instability fluting instability. In the case of the sunspot, where we have an inclined field of the magnetic field towards the non-magnetized region due to the funnel shape of the penumbra, this mechanism or the interchange instability is enhanced and can be driven further. Our study of the compactness, which compares the area with the circumference, is a measure of this fluting process, basically. Another possibility now to study how to study the stable or unstable situation of a sunspot was already proposed by Meyer, Schmidt, and Weiss in 1977. They proposed a 2D static model, as you can see it here, where they assumed the magnetized flux tube to be separated from the non-magnetized region by a layer provided given here as S, which forms a discontinuity and where the magnetic field would drop abruptly to 0. Therefore, this layer S has to keep an equilibrium condition between the pressure, the magnetic pressure and plasma pressure within the tube to the outside plasma pressure. Based on these conditions, they came up with a local stability criterion, which takes into account buoyancy by considering the difference of the density of the surrounding plasma to the plasma within the tube. And they considered as an opponent the magnetic tension forces and the independence of the radius of curvature given here. Meyer, Schmidt, and Weiss already proposed that the sunspot might be stable down to layers, down to a depth of 2 megameters. However, they were not able to verify this and or do any calculations for deeper regions because of their lack of knowledge of these regions. We have now the advantage that we have this nice simulation where we can apply the stability criterion too. And to do so, we had to come up with some additional adaptations, as our sunspot, due to its corrugated shape and also in general does not have such a nice outline in form of this surface S. And therefore, instead of using the boundary value, we determined spatial averages for the magnetic field and the density within the tube, and also for the averaged the region in the surrounding to obtain the density of the surrounding plasma for each of the depth positions which we had selected earlier. Besides this, for evaluating the equation, we need the inclination of the magnetic field towards the vertical, given here by He, and the radius of curvature. We now have to come up with something describing our surface S, and therefore we made use of the area of the corrugated flux tube and assume to have a circular flux tube with the same area, which gives us for each depth position and something like which we call equivalent radius. Applying an asymptotic fit, we can then calculate the inclination, which you can see here for the different depth positions with the dots being from blue to red in time, the color coding from blue to red in time, and the stars being the time averaged values. You can see that at the bottom of our analysis range, we have an almost vertical field, so close to 0. And towards the surface, for higher layers, the inclination of the field towards the vertical increases, where we then found an almost horizontal, where we find the almost horizontal field lines of the penumbra close to 90 degrees. The radius of curvature is shown here, and to give an idea what the radius of curvature is. So the radius of curvature is the reciprocal of the curvature. This means that for any straight line, which is either horizontal or vertical, the curvature is 0, and therefore the radius of curvature would be infinity. Therefore, we obtain for an almost horizontal field or an almost vertical field pretty large values for the radius of curvature. However, when the curvature is largest, we obtain here at 2.5 megameters below the surface the smallest radius of curvature. We can now use these values for the different depth position and the values we obtain for the magnetic field and the densities, and insert this into our linear stability criterion. If we evaluate this equation, we can find the layers of instability or stable condition for the flux tube. The reason why I put the inequality like this is because it makes it pretty easy to visualize the results, because for any stable conditions, we obtain positive values, while negative values yield an instability. The results are shown in this plot, where we see easily that down to approximately 1.75 or 2 megameters, we have a stable condition with individual time steps being here already unstable. However, there's no trending time. So these are totally arbitrary time values. For all deeper regions, the flux tube is unstable. The largest instability is localized at a depth of 3.125 megameters, while when going deeper, the flux tube approaches a marginal stable state. We can now use these results and combine them with the results we have from our study of the compactness evolution. Then this enables us to get a picture of the stable or unstable layers of the sunspot. To remember, the compactness was constant in time for a depth down to 1 megameter, and this agrees with the results of the linear stability analysis, where we have a stable condition down to 2 megameters. We can explain this by considering the linear stability criterion, which was derived by Meyer, Schmidt, and Weiss, as they described that buoyancy will stabilize the sunspot in these layers due to the horizontal orientation of the penumbra, where the less dense magnetized field lines lie on top of the way denser material of the non-magnetized surrounding region. Then, if we go deeper, we find that the smallest initial compactness is localized at a depth of 3.75 megameters. This also agrees with the linear stability analysis, where we have the largest instability at 3.125 megameters. We can still explain this by our linear stability criterion, as we see that buoyancy decreases within these regions, while the curvature increases, and therefore the radius of curvature, given here, decreases. However, we now find that when looking at the evolution in time, the fastest evolution happens at a depth of 6 to 10 megameters. We conjecture that this is caused by non-local effects, which are not considered in this linear stability criterion, which only considers local effects. And the non-local effect here is the anchoring of the field lines at the surface in the penumbra. So the field lines are tied together and kept in a certain range within the spot, within the penumbra, because of the buoyancy which stabilizes them here. This anchoring effect decreases with the length of the anchoring point, and therefore field lines in deeper regions are able to move more freely compared to, for example, in regions between 3 to 4 megameters. If we now go even deeper, below 10 megameters, we find that for the compactness, the evolution slows down or is slower. Which goes in line with the flux tube approaching here a marginal stable state. Also, this can be explained by the stability criterion, as the flux tube is more vertical here and less curved. In addition, we have to consider here convective time scales. If you remember the movie which I showed for the evolution, you could see that at depths between 10 megameters, the evolution of the whole structure of the flux tube, but also of the surrounding, was pretty slowed down. And therefore, any perturbation acting in this depth would need a longer time to be visible. We have now derived this nice picture of the different stable or unstable layers of the sunspot. but for the full evolution, we might have to consider the surrounding region as well and surrounding effects. One effect here might be radial flows, which are directed towards the flux tube of the sunspot and which might enhance interchange instability. You can see them here in a map of the radial flow field, where you have these pronounced dark patches which appear within the indentations and seem to really move inside here and cause the indentations to be deeper. In contrast to these radial inflows, we have a stabilizing effect caused by the mode flow. This is this strong red outflow pattern, which you see in basically all layers besides at the surface where you have granulation dominating, which moves away from the spot. Matthias found in his study that the mode flow leads to the void of downflows and reduced RMS velocities. Both of these effects, so the void of downflows and the reduced RMS velocity, keep the flux tube together and stabilize it as any submersion of feed lines or transport away is prevented. However, if we consider that we see sunspot decay and lose flux, the final step needs magnetic flux to be transported away from the spot. Coming back to the surface and looking at this sunspot at the surface, we see that this corrugation process is not visible there. And Matthias also found that the area and the magnetic flux of the sunspot is constant in time, which, based on the general aspect of sunspot decay, would mean that we don't have a decaying sunspot here. However, what Matthias found is that the area of the umbra decreases in time while the magnetic flux is transferred from the umbra into the penumbra region. You can see this here on the right side on the upper panel, where you can see for the first and the last time step of our analysis. And you can see that the umbra is here way larger in comparison to for the latest time step. This agrees with a study of an observed sunspot by Martin Benko and his co-authors, and they studied or found that the vertical component which separates or defines the boundary between the umbra and the penumbra moves inwards, giving space to the penumbra to take over the region, even before the sunspot loses magnetic flux or decreases in total area. Besides this, we conjecture that light bridges might be tracers of this process which we see in the deeper layers, as we can correlate them to our indentations, as you can see here. So these finger-like structures which penetrate into the umbra and which become stronger in later times can be nicely correlated with the indentations we see down here. And these penetrate down to regions of around 5 megameters. This agrees with a study of Matthew Panya, who found a similar correlation in his simulations, where he studied the formation of the penumbra. So in summary, we have a simulated sunspot, which is in an observable stable stage. However, we see that it becomes corrugated below the visible surface, and which is caused by interchange instability, which leads to a degradation of the flux tube at its boundary. This interchange process is enhanced or further driven because of the curvature of the field lines. We conjectured that this process is the onset of sunspot decay, as this degradation leads to a weakening of the magnetic field within the flux tube, especially in these indentations, as we have seen in depths of 3 to 5 megameters. This will in time cause the corrugated structure, also this highly corrugated structure will in time cause the confinement which is given to the due to buoyancy and due to the mode flow to fail and enable the development of turbulent flows. And these might then be able to drag away field lines or submerge them and cause a loss of magnetic flux from the sunspot, which is observable and at the surface. Besides this, we conjectured that we have observable traces which can be seen earlier before the sunspot even decays, which are the transformation of the umbra to penumbral area and the development of light bridges. In total, we summarize that a sunspot decays bottom up. That's it. Thanks for your attention.
Thank you very much, Anna, for very nice presentation. We now open for questions. So, questions from audience? So in the meantime, I have a question. When you get the corrugation, you initialize with a certain corrugation, and then in the course of the evolution, you get the stabilized corrugation, or you do not initialize it, but it arises due to instability.
Sorry, can you repeat? I don't.
So my question is, when you obtain corrugation of sunspots,
Yes.
do you initialize with a certain corrugation, and then in the course of the evolution, it gets stabilized to a stable corrugation, or it automatically develops due to instability?
You mean what happens later in later times?
Yeah.
This is so, I mean, we only have this 30 hours analyzed. And there it seems that due to this weakening, which we see, the flux tube might get separated in time. However, as this simulation ends, then we don't know what will happen in later times for sure. What I'm doing at the moment is looking at a simulation of a naked spot, so which has already lost its penumbra. Yeah, maybe this will give us further insight.
Okay, thank you. Yu-Hong?
Yes, for your low boundary condition, do you tie the foot points of the flux tube so that it doesn't allow it? I mean, what's the foot point at the low boundary? And also, does the process of this decaying consistent with the observed time scale, as you see in your process of decaying due to the fluiding and effects?
So the first question, I think it's not tied, but maybe Matthias can say if I'm correct. So the field lines are not kept together at the foot points.
Yeah, so the bottom boundary is symmetric boundary condition for both all three mass flux components and all three magnetic field components. So the magnetic field is free to move around as it wishes to do.
Okay.
And for the second question, which was about the times.
Yeah, is it consistent with observed times, lifetime?
I mean, this is the problem basically. So what we see from a visible, so what we can compare with observation is a stable sunspot. We do not see the sunspot decay at the surface. The only thing which we could compare would be the change of the the change of the area of the umbra or of the magnetic flux from umbra to penumbral region. I only know of this study by Martin Benko, which is the only I know who have a stable sunspot, which then later decays.
Okay, thank you. Actually, another question: are you going to have plans putting in twist into the configuration? Whether that would change the result? You have any plans on?
Oh, until now, not yet.
Okay.
We would have to ask Matthias how this would work.
Okay. Thank you.
Maybe I can answer that question. I mean, I have done some experiments with twisted sunspots, but the challenge is you really have to impose boundary conditions which maintain the twist. I mean, otherwise it just untwist, right? You have to put some boundary conditions which can hold some stresses at both the bottom and top boundary, since you don't have a corona above and a deep enough convection zone with enough mass in there to kind of prevent the untangling of the sunspot.
Right.
Any other questions from audience? Okay, so if there is no more questions, let's thank our speaker again for a very nice talk. Thank you.
Thanks.
Thank you.
I'm not smart enough to ask any questions.
That's not true. I know.